All right, everyone. Welcome to this morning's webinar, Tech Tuesday, Introduction to 3D Scanning. My name is Chris Himberg. I work here at CamLogic, and yeah, let's get rolling. So first, let's familiarize everyone with CamLogic. CamLogic has been in the CAD/CAM CAE space for over 35 years. The company was established about 16 years ago, initially focused on CAM, servicing mainly the tool and die shops in our area. As the market evolved, CamLogic has evolved with it. Interestingly, working our way backward from manufacturing back to the conception of the idea or design. Because we started toward the end of the process, worked our way back to the beginning, CamLogic has the fundamental knowledge of what has to be done to assure that each step of the process will result in a product that will actually work or fit into the next phase of development. CamLogic has chosen to represent software and tools that enable our customers to fulfill full cycle of product development. And we consider ourselves integrators and partners for our customers, not just resellers, and we take tremendous pride in that relationship. CamLogic employs a three-legged stool technology. We partner with Siemens, offering the complete integrated Siemens portfolio for design, machining, analysis, and data storage and retrieval. On the 3D printing and rapid prototyping side, we partner with 3D Systems, and what we're here to talk about this morning for the 3D scanning, we partner with Romer, Creaform, and Steinbeckler for, again, the 3D scanning for inspection and reverse engineering. So, now that we've touched on that, let's move ahead to 3D scanning. But right before we get to 3D scanning, let's talk about where it all began. And it sort of all began with the CMM, or the Coordinate Measuring Machine. It was originally developed for production verification. When items were produced, they wanted to make sure, obviously, that what they were producing was within spec. We see here pictured a 3-axis coordinate measuring machine, and they're obviously they were designed to be accurate. So we're talking, down to thousandths of a millimeter, 1-2 microns for these machines, and some of them even less than that. They are big and they are very heavy. They are designed to be used in conjunction with a giant slab of granite, which minimizes the effects of any temperature variations. Because these machines are so accurate, slight variations in temperature will affect the measurements. Another drawback for the CMM is that obviously the parts have to be brought to the CMM for measurement. So these machines certainly have their place, and again, this is sort of where everything began, but we are moving forward with technology, and here's what's now available. We still have the CMM sort of idea with ARM-based probes and handheld probes where you're only capturing one point at a time. The probe obviously has to be touching the object being measured, and button is pressed, and then that point is captured in 3D space. We move along to the right to the laser scanners, where again you have the ARM-based laser scanner that is similar to the ARM-based probe, except that you have a laser head attached to the end of the arm. And we also have handheld laser scanners where you have digital cameras that are in the handheld unit that look at reflective positioning dots that need to be placed on the object so that the scanner can orient itself in 3D space. Over on the far right, we have your structured light scanners. At the top, that's a mounted unit, and at the bottom, we have handheld. So the structured light, you have some sort of light source that's going to be projecting a known pattern or image onto the part, and then you have a digital camera, usually 1 to 3 digital cameras that will look at that projected image or pattern and be able to describe the surface looking at the deformation of that pattern. So a little more in depth, again, the portable CMM is basically a touch probe and a trigger that captures the point. So the arm-based, you have encoders at each joint in the arm. It's almost sort of the reverse of a robot arm, where with the robot you would have obviously servo positioning motors in each joint that would move the arm for you. Instead of motors in each joint, we have encoders, and that is what describes the point's position in 3D space. The base of the arm is considered 0, 0, 0, X, Y, and Z, and because of that, obviously we cannot afford any movement whatsoever between the base of the arm and the part. Obviously, if we have any movement, then now our measurements are off. The main advantage to this, obviously being a portable CMM, it can be brought to the part. So here in this picture we actually see a magnetic base. So if you have a huge tool or die sitting in a press, you can actually take this to the tool, attach the mag base to the part, and probe it right there. Moving down to the handheld, this actually requires a separate piece of tracking equipment. So you can see sort of over in this picture on the right, that fellow there with the handheld probe, you can see the positioning dots are actually on the probe itself. So your positioning equipment is typically 2 cameras that will be able to position the probe relative to the part being measured, which itself will have positioning dots as well, and measurements can be taken. This particular style of probing is well suited to unstable environments because you have positioning targets on the probe and on the part. If the part moves, there's really no problem with that because the camera can keep track of both the probe and the part from the positioning targets. And moving on to the laser scanners, where we start capturing more than one point at a time. The laser is basically, the laser scanners are just a laser, either a point or a line or maybe even a crosshair in the handheld world, and a digital camera or two. So again, we have a light source that is being projected onto the part and some sort of camera that is capturing the deformation of that light source on the surface of the part. If this slide looks similar to the last one, it's because it is. It's pretty much the same. Your arm-based laser scanners work very similar to your arm-based probes, again with the exception that you have a scan head at the end of it instead of a probe. So your handhelds are again very similar. You're going to have positioning targets on the part, as you can see over in the picture on the right, and again suited to unstable environments because of the fact that the positioning is done from the targets that are actually attached to the part. So again, if the part moves, no big deal. And again, with the ARM-based system, if the part moves, it is a big deal. So keeping that in mind. And structured light scanners. These use a what we sometimes call a fringe part, and then again a digital camera, typically 1 to 3 cameras that will capture the deformation of that image on the part. The image over on the right is a very good example. You can see that that fringe pattern is being projected onto the wheel. And again, the scanner knows exactly what that fringe pattern is supposed to look like had it been projected onto a completely flat surface. So when it's projected onto a curved surface, it's able to see the deformation of that pattern and then describe that to the computer to make a 3D surface. Targets can be used with these systems, although they are not necessary. Again, a big advantage is that the scanner can be brought to the part. So again, the example of a very big die or tool, instead of having to crane that over to the scanning system, the lightweight scanning system can be brought to the part. The one drawback to these systems is part preparation. They typically need to be white. If they're not white, they need to be sprayed, and a matte finish is desirable. Your handheld systems, very similar, except that they're handheld. They're not quite as accurate as the mounted systems, and again, these are suited to more unstable environments where the part can move relative to the scanner, and we don't really have an issue with that. So one idea that comes up a lot when we're talking about 3D scanners is accuracy, precision, and resolution. So going back to high school chemistry and or physics, the difference between accuracy and precision, as we can see here with this dartboard example, the image on the left, we have good accuracy and good precision because we have the 3 darts that are close to the bullseye, which represents accuracy. The bullseye is what we're aiming for. And good precision. We have good grouping of the darts. The middle image, we can see that we have poor accuracy because we've missed the bullseye completely, but we still have a good grouping, so that represents good precision. And then on the far right, we have poor accuracy and poor precision. Not very close to the bullseye, and they're pretty much scattered all over the place. So the third piece of this puzzle is resolution. And resolution in this dart example would be represented by the number of darts. Resolution can also be thought of as the fineness or the detail of a measurement. So when we're talking about 3D scanners, everyone says, well, I want the highest resolution I can get, right? Well, generally speaking, I suppose so, yeah, but obviously cost is going to play a part. So higher resolution does not necessarily increase the accuracy or precision. Those are independent. But higher resolution will increase the confidence in your measurements. So keep that in mind if you're looking for a 3D scanner, and when you're looking at the spec sheet, just keep in mind that maybe the numbers on that spec sheet may not tell the entire story. So if you are looking at a 3D scanner, what's the right scanner? Well, it completely depends on your application. And as with most things, there is no silver bullet. We don't have one scanner that's going to meet every single need for every single application. So we will just touch on some of the pros and cons for some of these technologies. So first up is the laser scanner. Whether it's ARM-based or handheld, these pros and cons will apply for both. The laser scanners are typically more portable. They require less part preparation, being that, let's say you have a casting of a steering knuckle or something like that. You could actually take that raw casting and scan it without the need for any painting or any other surface preparation. And because it's a laser and it's a very specific spectrum of light that's being projected, these systems are typically less sensitive to ambient light. Obviously, that is a concern because we're dealing with a digital camera. These scanners, although are generally less accurate, they are generally lower in resolution, and they generally generate higher noise. Noise being unusable data or data that isn't really there. That's a big concern with scanning technologies in general, and something that the laser scanners are particularly susceptible to. So, moving on to the structured light scanner. These are generally more accurate. They are often higher resolution as well. So again, the fineness and detail of your scans will be higher than with other technologies. And we generally have lower noise. So again, we're going to get a crisper, more clean data out of this type of scanner, which means that we have less work to do, less cleanup work to do at the end of the day, which is nice. Unfortunately, though, these scanners are generally not as small or as portable as some of the other technologies. They are more sensitive to surface finish, so you are going to have some prep work up front. You're going to need to be spraying some white powder or some white paint on parts, generally speaking, and they may require some specific lighting. Some of the new structured light scanners that are coming out are actually using blue light as opposed to white light. That will reduce the requirements for specific ambient lighting, but again, they are still more susceptible to that than the laser scanners. So some common applications for 3D scanning. Inspection is probably number one. Again, that's kind of where this all started with the CMM, so that's sort of where we end up. Inspection falls under metrology. Metrology is basically the science of measurement. So a lot of metrology tasks revolve around 3D CAD comparison or 2D cross-sections and 2D dimensions. You can see down in the bottom right we have a 3D CAD comparison of a crankshaft. So that allows us to see the deviation in the part that was produced against the nominal CAD data that was imported. Again, above that we have the 2D cross-section of a part. So we can take the cross-section of the CAD data along with the corresponding cross-section of the scan data and compare the two and actually pull dimensions from the scan data or CAD data and be able to do a pass-fail for specific features in this part. We also have GD&T, which generally falls under quality control. Geometric dimensioning and tolerancing, something that was developed to understand whether or not a planar surface is truly planar or the tolerance within that plane has to fall, or cylindricity, and things like that. So that's a lot of what we deal with when we're talking about inspection. So if you're looking to do some inspection, what sort of scanners are you going to be looking at? Well, chances are you're going to be looking at an arm-based laser scanner or a structured light scanner. The reason, for the most part, is accuracy. Obviously, if we're talking about inspection, accuracy is paramount. So we see here that your typical laser scanner is going to be accurate to about 60 microns, and your structured light is going to be all the way down to 4 microns. So that's a pretty big jump. And the 0.004 millimeters, we're really starting to approach the accuracy of CMMs that are out there. Obviously, calibration is something that needs to be discussed as well. If your equipment is not properly calibrated, then your accuracy really starts to go right out the window, and your measurements, you really can't have much confidence in your measurements. The precision of your equipment is going to rely quite a bit actually on your environment. As we mentioned before, temperature and vibration, unstable environments, these things must be taken into account when we're talking about precision. We can actually have a temperature swing such that it affects the length of a scanner arm, thus affecting the accuracy. So again, these things need to be taken into account because we're dealing with such minute measurements. And again, resolution comes into play. So we're talking about 0.07 millimeters for laser, 0.02 for structured light. So again, your structured light scanners are going to be generally higher resolution, more detail, crisper definition. So very well suited for inspection. And reverse engineering. This is something that comes up a lot when we have a broken part or a part, say in Jay Leno's case, for an old steamer where the part just simply isn't manufactured anymore, and the one that's there may be the only one in existence on the face of the earth. But if it breaks, you still need to be able to make another one. So that's where we're going to be talking about an as-designed reverse engineering process, where we may have incomplete scan data, but because we are going for design intent, we can assume that planar-like surfaces will become planes, cylinder-like surfaces will become true cylinders in the CAD world. So we can take some design liberties with the information that we have and be able to reverse engineer an entire part in the CAD world and end up with a fully parametric 3D model at the end of the day. Your other option is to go with an as-manufactured reverse engineering process. This process will give a more true-to-life representation of the part that's scanned. Typically, your surfaces are going to be comprised of NURBS surfaces, or non-uniform-rational B-spline surfaces. These surfaces are basically created by using freeform curves that a surface is then swept through. And because of that, your imperfections that may be on the part are kept, and certainly the original shapes are maintained even if there is deviation from what would be considered a perfect part. So again, as manufactured, more true to life, and sometimes that's more desirable than, say, an as designed or true design intent reverse engineering. So what scanners would we be using for reverse engineering? Well, obviously the ARM-based laser scanner and your structured light scanners are going to be perfectly well suited for reverse engineering. They're good enough for inspection, and obviously inspection is very demanding on the scanner. Reverse engineering perhaps a little bit less so, so obviously the scanners that meet the inspection criteria will work for reverse engineering. But we also have your handheld laser scanner and your handheld structured light scanner. These particular technologies are going to be perhaps not quite as accurate, or maybe not have quite as high resolution as your other scanners. But again, because we're dealing with a reverse engineering process, say, as designed, where incomplete data is acceptable, then these scanners are perfectly well suited for that type of application. Again, calibration certainly comes into play with any of these technologies, and again, your precision is going to be dependent on your temperature and the different environmental variables that are present. The handheld scanners, those actually need to be calibrated as you use them, because the heat from your body is radiating into the scanner, and yes, it affects the precision. So those do need to be calibrated. As you can see at the bottom on the left, we do have much lower resolution for the handheld structured light in particular. But again, based on the requirements of your application, a lot of times that resolution is completely acceptable. So that's pretty much it for our introduction into 3D scanning. This was a little short and sweet, but hopefully we got some information out there, and be glad to open this up to any questions. Feel free to type them into the window, and we will address them as they come in. All right, well, looks like we don't have any questions. That's fine. So thank you all for attending. Again, my name is Chris Himberg, an applications engineer here at CamLogic. My contact info is on the screen. Please, if you have any questions or want any information about 3D scanning, do not hesitate to contact myself or any of the staff here at CamLogic, and hope everyone has a great day. Thank you.